All right, so we finished the last lesson from Unit 6 on bonding, talking about hybridization. This tells us the types of orbitals that the molecules or the atoms are going to bond with in order to form these molecules. Today, or this lesson, is talking about what those actual bonds are and what they look like. So, we have two different types, and I know this is a little bit fuzzy, but this is in your notes and it's a little bit clearer. We have two different types of bonds. We have sigma bonds and pi bonds, all right? So sigma bonds are what happens in a single bond. So anytime you see a single bond on a Lewis structure, like this guy, CH4, lone little methane, this bond right here is a sigma bond. There's free rotation, so if you notice when you look at molecular structures and actually the models, you can rotate around that bond without breaking it. And sigma bonds are characterized by how they overlap. So in a sigma bond, they are overlapping by head-to-head overlapping. So you can have any type of orbital overlap. If it's overlapping the head-to-head, that's a sigma bond. So like here in this picture, we could have an s orbital and an s orbital overlapping. Or in the next one, you can have an sp2 orbital overlapping with an sp3d2. It really doesn't matter what type of orbitals they are as long as they are overlapping head to head. All right, so now if we look at pi bonds are only made by unhybridized P's. These unhybridized p orbitals will sideways overlap and create what is called a pi bond. So pi bonds are found in double and triple bonds, and what's interesting about them is there is no rotation about those bonds. So if you look at a model kit, and if you have a double or triple bond, you cannot rotate those atoms around that bond. It'll break it. So looking at the three types of bonds we have single bonds, double bonds, and triple bonds. So single bonds consist of just sigma, okay? And you determine this from the Lewis structure, okay? Double bonds, every single type of bond, single, double, or triple, consists of a sigma, if you notice, okay? Because there's always a head-to-head overlapping of those hybridized orbitals, or really any type of orbital, but typically those hybridized orbitals. Single bond is just sigma. Double bond is a sigma and 1 pi, and then triple bond is sigma and 2 pi's. So you need to know this stuff here, because when we draw the Lewis structures, you might also be asked, hey, how many sigma bonds does this molecule have? How many pi bonds? All right. I'm going to go into more of how those bonds actually overlap and how we can figure it out from the structures drawing the different orbitals. You are not going to be responsible for drawing the different orbitals on Lewis structures, but this might help you understand why a little bit more instead of just memorizing a single bond is 1 sigma, a double bond is a sigma and a pi, and a triple bond is a sigma and 2 pi's. Okay? All right, so again, you're not going to be responsible for these, but this might help you understand it. So, ethane. Let's draw ethane real quick. Just Lewis structure. You should know how to do this. So ethane looks like this. All right, so ethane has 2 C's, and I'm going to actually draw out the orbitals around each carbon and show how they overlap and how they form their sigma and possibly pi bonds. So looking at the carbon on the left, it has 4 things attached to it. And when you have 4 things attached to it, that's sp3 hybridization. So we're going to draw, it's going to have 4 sp3 hybridized orbitals, and that's what I'm drawing here. All of these guys are sp3. And the other carbon, if you notice, has the exact same hybridization. It has 4 areas of electrons around the central atom, so it also has 4 sp3 hybridized orbitals, which I'm drawing in now. Now notice here, this sp3 orbital overlapped with this sp3 orbital. There's a head-to-head overlapping, so that just made a sigma bond. All right, now, but what about all those hydrogens? Well, hydrogen does not undergo hybridization. Hydrogen, the atom, just has one lone little electron, and it's only on the first level. It's only the s orbital. There's no other orbitals to throw in a punch bowl and make it hybridized, so it just has that s orbital. So that overlaps. That's an s. Each of these, it bonds to the hydrogen. That should be straight up and down, but I ran out of room. All this overlaps with that hydrogen, with that one s orbital that hydrogen has. So each one of those overlapping has made another sigma bond. So sigma, 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 sigma. So we have a total of 7 sigma bonds, which you could have counted from the fact that there were 7 single bonds in this molecule, but this shows how the overlapping occurs and how those sigma bonds are formed. All right, so moving on, let's talk about ethene. Ethene looks a little bit different because it has a double bond. Looks like this. So since the number of areas around the central atoms, the carbons, have changed, it's decreased, the hybridization's a little bit different than it was in ethane, which had all single bonds, and each carbon had 4 areas of electrons around it. Each of these carbons only has 3, so each carbon has, each carbon has sp2 hybridization around it. So like each one's around sp2, so around each one of these carbons we have 3 sp2 orbitals. sp2, sp2, sp2. So around this carbon, it's all sp2 as well. sp2, sp2, sp2. 2. There we go. And remember, the bond angle among these sp2 hybridized orbitals, that's 120 degrees. That's what makes them the most happy, the most equally distributed among the carbon. So we have an overlap here. That's a sigma bond. But we cannot forget something. When we have an sp2 hybridized, or when we've made those hybridized orbitals, we have one unhybridized p orbital. One unhybridized p. And where's that? That is right here. Didn't get thrown into anything, didn't get thrown into the punch bowl, didn't get mixed in with the S and the other P's. It was left alone. It's still there, but it was, it's unhybridized. So what's going to happen is we're going to have a sideways overlap between these unhybridized p orbitals, and they're going to kind of bend and stretch so that the top lobe to the top lobe, they kind of bond, and the bottom lobe to the bottom lobe bond together, making a pi bond. So this is my little pi bond. So just that double bond between the 2 carbons, we have 1 sigma and 1 pi. Now, again, just like with ethane, we have these hydrogens that are single bonded to the carbons. Each hydrogen, remember, bonds with just this little s orbital, and it's a head-to-head overlap with that sp2 hybridized orbital. So those are all sigma bonds as well. So this gives us a total of 1, 2, 3, 4, 5 sigma bonds and 1 pi bond. And again, remember, you do not have to draw this picture showing the overlap of the orbitals. You can look at just the Lewis structure. You see that we have 1, 2, 3, 4 single bonds, and then 1 double bond, which consists of 1 sigma and 1 pi, and all single bonds are just 1 sigma. So you can get this number, these numbers, the 5 sigma and 1 pi, from the Lewis structure without drawing the overlapping, just showing you how it's done, how it occurs to help you understand it a little bit better. All right, so we have one last example, and this is ethine. Ethine has a triple bond between carbons. All right, so this time each carbon only has two areas or two things attached. So the hybridization for each carbon is going to be sp. So if I were to draw the two carbons again with their orbitals, drawing them overlapping, so each one only has two sps coming off of it. That's an sp and an sp. And see how the sp orbitals in each thing, the bond angle here is 180 degrees, so we know this is going to be a linear molecule. Now, just like with double bonds, when we had an sp2 hybridized orbital, like here, I'll go back to it, in ethene, we had that one unused, unhybridized p orbital, because we only used two of them in the hybridization. With this one, we have two unused p orbitals, or two unhybridized p orbitals, and they are on the carbon atom. There's one. I'm going to draw the other one in a different color. It's not, it's like a three-dimensional thing. They're going off to an angle a little bit. So these unhybridized p orbitals are still going to overlap. The orbitals in the same direction are going to overlap with the orbitals in the same direction. So the ones I drew kind of along the y-axis, the blue, they're going to overlap. And then the ones I drew in orange, they're technically in the z direction, but since this is a two-dimensional thing, it's kind of hard to draw that. So this overlaps and this overlaps. All right, so we have, the thing that I drew in blue, that's one of our pi bonds. The thing I drew in orange is another one of our pi bonds. And then here in the center, we have that purple overlap, which was our sigma bond. And then we have the two hydrogens, which are using their s orbital to bond with the sp. So there are two more sigmas. So we have a grand total of 1, 2, 3 sigmas and 2 pi bonds. Again, you can find that from the fact that there are two single bonds in this molecule from the Lewis structure, and there's two of our sigmas, and then a triple bond is 1 sigma and 2 pi's. All right, so now I'm going to show you a problem where you might have multiple things asked about a large molecule. So we've got this guy here drawn out. So the first question is asking, what are the approximate bond angles about each of the two carbons, and what are the hybridization of the orbitals on each of them? So we want to know bond angles and hybridization. So we have two carbons. We have the first one, which I'm going to put an arrow up to as orange, and the second one I'm going to put as green. All right, so my first carbon, there are 4 things attached to it. So that means that the hybridization, which I'm going a little bit out of order in the problem, but the hybridization would be sp3, because 4 things leads to 4 sp3 orbitals. And whenever you have sp3, the bond angle, or the approximate bond angle, is 109.5 degrees. The second carbon, we have 3 things around it, the double bond to oxygen, the single bond to oxygen, and the single bond to the other carbon. So this hybridization is sp2, and the approximate bond angle is 120 degrees. All right, looking at the next one, the next problem, I should say, what's the hybridization of the orbitals on the 2 oxygens and the nitrogen, and what is the approximate bond angle of the nitrogen? So we have the 2 oxygens. I have the double bond to oxygen I'm going to do in purple, whatever color that is. The other one I'm going to make red. I had to change colors. And then the nitrogen I'll do in blue. Oh gosh, I'm just thinking when you look back at this picture, if you see this at the very end, you're going to be so confused why there's all those arrows. All right, so let's do the thing I did in, what color did I do? Purple. There we go. The purple oxygen. This is the one that's double bonded. So it is, sorry, I lost my train of thought. that oxygen, it's kind of hard to see, but it has 3 things around it. It has 2 lone pairs and that double bond. It has 3 things. Whenever you have 3 things, that's sp2. Even though the lone pairs aren't bonding with anything, it is considered to be an area of electrons. So it's sp2. It doesn't ask about the bond angle for the oxygens. All it asks is for the nitrogen. So that's all we need to know is sp2. The second oxygen, the one that I'm doing in red, it has 4 things around it. 2 bonds and 2 lone pairs. So that's sp3 hybridization. And then the nitrogen has, it's connected, so I'm going to draw this up here. It's technically bonded to 2 hydrogens, a carbon, and then it has a lone pair. That makes it have 4 things, which is sp3. And the approximate bond angle, for any time it's sp3, it's 109.5 degrees, but that lone pair makes that bond angle go down just a little bit. And then the very, very last question is asking just how many sigma and pi bonds are there. Now, you could go through and do what we did with the last little bit and draw all the overlapping, or you can just count. So, sigma bonds, remember those come from single bonds, and then sigma bonds come from any sort of bond no matter what, if it's a single, double, or triple bond. So we have nitrogen that's attached to 2 hydrogens. There's 2 bonds. That nitrogen is attached to another carbon. That's a 3rd bond. So right now we're at 3 sigmas. That carbon is attached to 2 hydrogens. There's 2 more sigmas, so now we're at 5. That carbon's also attached to another carbon, which is another sigma, so now we're at 6. That carbon that's double bonded to the oxygen, that's a sigma. It's single bonded to another oxygen, so that's a sigma, so I'm at 8. And then that oxygen's bonded to another hydrogen, so I'm at 9 sigma bonds. All right? And then the double bond, we already accounted for the sigma bond that's in that double bond, but it also has a pi bond. All right, and then the last one, I don't want to do anything more with the bond angles, but let's just do the hybridization. So we have these 4 central atoms. Come on, purple pen, work, thank you. So this first carbon, it has 4 things attached, so that's sp3. The second carbon has 3 areas around it, so it's sp2. This third carbon has 4 areas around it, so that's sp3 again. And the nitrogen has 4 things attached and 1 lone pair, 3 things attached and 1 lone pair. That makes 4 areas of electrons, so that makes it sp3. And then if we were to ask sigma and pi, let's just go ahead and count those up, just more practice. Remember, every single bond counts for a sigma, so we have, I'm going to mark them as I go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sigmas. And then this double bond also is 1 pi. All right? So you need to know how to figure out the hybridization, which we did last class, or 2 classes ago if you're my A-Day kids, because we had that lovely day when we should have had a snow day. And then you need to be able to know from the Lewis structure, count how many sigma bonds and how many pi bonds there are. Now you can just memorize the stuff, but hopefully with me showing you how the orbitals overlap and form the bonds, it'll help you understand it a little bit